So this is very important. Listen. As far as diatomic molecules are concerned, diatomic molecules. Observe this carefully. Homodiatomic molecules. Homodiatomic molecules. These molecules are microwave inactive. They do not show any microwave spectrum because permanent dipole moment is 0. Homodiatomic molecules, they are also inactive in IR inactive. Okay, since there is no permanent dipole moment, during vibration, dipole moment do not change. Okay, so homodiatomic molecules are both microwave inactive and IR inactive. But homodiatomic molecules are active in Raman. Okay, so for homodiatomic molecule, we can take rotational Raman. Rotational Raman's active, and homodiatomic molecules are also vibrational Raman active. Vibrational Raman active. Okay? Observe carefully, this is very, very important. In the case of heterodiatomic molecule, you know very well, heterodiatomic molecule. Yes, this molecule is microwave active, right? You can take microwave spectrum, okay, and you can find the rotational constant, right? From the rotational constant, we can find the internuclear distance, also called bond length. Heterodiatomic molecules are microwave active. I put this stick symbol, just showing you the molecule is active. Then heterodiatomic molecules, they have permanent dipole moment. During vibration, dipole moment changes. So heterodiatomic molecules are also IR active. Okay? And heterodiatomic molecules are also Raman active. This is a very, very important information. Keep this in mind. Okay? Right, so as far as diatomic molecule is concerned, for homodiatomic molecule, yes, the rotational, the Raman spectrum is the best spectroscopic technique to analyze the bond length or to measure the rotational constant of the molecule, etc. For heterodiatomic molecule, we have many spectroscopic techniques. Okay, so this is fundamentally important information. Keep that in mind. When you come to polyatomic molecule, okay, mostly they are active in microwave, IR, as well as in Raman, right? And you might have heard about this called you might have heard about this mutual exclusion principle. Mutual exclusion principle. Suppose if a molecule, right, polyatomic molecule specifically, if a polyatomic molecule possesses center of symmetry, I mean center of symmetry. If polyatomic molecule possesses center of symmetry, then the vibrations or the normal modes which are active in IR, okay, those modes are inactive in Raman. Okay, if molecule possesses center of symmetry, then let me write like this: normal modes of vibrations, IR and Raman, I'll put like this. If the Raman modes of vibrations are IR active, then those vibrations, okay, those particular vibrations are inactive in Raman. Similarly, the normal modes of vibrations which are active in Raman are IR inactive. This is what we call as mutual exclusion principle. Right? The vibrations which are active in IR are Raman inactive, and the vibrations which are active in Raman, okay, they are IR inactive. Right? Yes, keep this in mind, very, very important. Right? See, suppose I'll take a carbon dioxide molecule. It's a very simple molecule, possesses center of symmetry. See, this molecule possesses center of symmetry. And you know very well, it is a linear triatomic molecule. So, number of normal mode is 3n minus 5. 3 into number of atoms in one molecule is 3 minus 5. 3 into 3, 9. 9 minus 5 equal to 4. So, this molecule possesses 4 normal modes of vibrations. 4 normal modes of vibrations. Now, the question is, out of these 4, okay, whether all the 4 normal modes are active in both IR as well as Raman. Okay, what mutual exclusion principle is? What mutual exclusion principle says is that since the molecule is a centrosymmetric molecule, vibrations or normal modes which are active in IR are Raman inactive. For example, listen, first I will take symmetric stretching normal mode. Symmetric stretching vibration. Symmetric stretching vibration. In symmetric stretching vibration, change in dipole moment during vibration, right? It is actually 0. During symmetric stretch, okay, dipole moment, right, does not change. d mu 0 means dipole moment is not changing. Therefore, this symmetric stretching vibration is IR inactive. Whereas, during this vibration, polarizability of the molecule d alpha, during the vibration, d alpha, it is not equal to 0, it is changing. Therefore, so this is for IR and the next information I am giving for Raman. Therefore, this vibration is Raman active. Second mode of vibration called antisymmetric, let me write here, antisymmetric stretching vibration. In antisymmetric stretching vibration, dipole moment changing, okay, dipole moment changes during vibration. Therefore, it is IR active. Whereas, the vibration, during the vibration, polarizability does not change. 0 means no change. Since polarizability is not changing, this vibration is Raman inactive. Okay, so the vibration which is IR inactive are Raman active, and the vibration which are IR active, they are Raman inactive. Is this clear to all? Listen, in the last class I have told you what is Raman shift. Raman shift is nothing but the difference between scattered radiation frequency minus incident radiation frequency. Sometimes instead of incident radiation, people call this as exciting radiation. Okay, excitation radiation, all are one same thing. So scattered frequency minus incident frequency. This difference may be positive or negative, but we usually take magnitude. And remember, this Raman shift, it depends on the nature of the substance. The Raman shift depends on the nature of the substance. Meaning, it depends on the gap between adjacent rotational level, gap between adjacent vibration level. It depends on the nature of the substance. But this is very, very important. Raman shift is independent of the frequency of the incident light. Okay. Suppose if I use 1000 centimeter, suppose if I use 1000 centimeter inverse incident light. Okay. And see, this is the Rayleigh line. Suppose if we use 1000 centimeter inverse light, we get a Stokes line here, suppose, and the Raman shift, suppose if we measure the Raman shift, right, let the Raman shift be say 800 centimeter inverse. For example, I used 1000 centimeter inverse radiation. Now, this is the Raman shift, okay. Now, for the same compound, instead of using 1000 centimeter incident light, if I use suppose 2000 centimeter inverse, 2000, right? If I use 2000 centimeter inverse, I'll get the Stokes line. But if you measure the Raman shift remains the same. Observe carefully. Raman shift is independent of the incident light. It depends only on the nature of the rotational states, or how the rotational states and vibrational states present in the molecule. It depends on the molecule. It does not depend on, okay, the frequency of the incident light. This is very, very important. So, that is induced dipole moment. When you expose the molecule to electromagnetic radiation, a dipole is induced. That induced dipole moment is equal to polarizability of the molecule times the electric field that we apply. Or I can write alpha is equal to induced dipole moment by E. Okay, this is the formula for alpha, polarizability. What is actually polarizability? What is the definition? It is nothing but induced dipole moment per unit electric field. What's the definition? Polarizability is polarizability of a molecule is the induced dipole moment. Is the induced dipole moment. Okay, induced dipole moment created or produced. Induced dipole moment produced per unit electric field applied. Per unit electric field. Yes, this is the definition for polarizability. If you put E is equal to 1, E equal to 1 means unit electric field. Okay. When you apply E equal to 1, then whatever induced dipole moment arises in the molecule, it is nothing but polarizability of the molecule. Okay, this is actually the mathematical definition. Now, what is the unit of alpha? Listen carefully. Dipole moment unit is ESU centimeter. Electric field unit is ESU per centimeter square. ESU cancel. Centimeter square, if you bring it to the numerator, it will become centimeter square. This is centimeter power minus 2. When it comes to numerator, it becomes centimeter square. Centimeter square into centimeter becomes centimeter cube. Remember, polarizability has the unit of volume. Polarizability, okay, has the unit of volume. Okay, take note. Listen, suppose a polarizability exists like this. Usually it looks like an ellipsoid. See, this is not a two-dimensional, this is three-dimensional. It looks like egg shape, egg. Okay. You take the center of this shape and draw a straight line to the surface. Listen, this length R, okay, this length R is actually inversely proportional to polarizability at this point. Okay, at this point, polarizability is alpha, then R is inversely proportional to the square root of alpha. What is meant by that? Listen, if alpha is small, then the polarizability distance is large. Okay, so if this is the polarizability ellipsoid, right? Then if the length, see, if the polarizability at this point is high, if polarizability is high, then R will be small. Okay, what I am trying to say, let me use a different paper which I will show you. I'll just give you the meaning for the polarizability ellipsoid. This is very simple actually. Very easy to understand. Listen, let me write. Suppose I have a polarizability like this. Okay, polarizability ellipsoid. Now listen, from this center point, you take a point here and draw a line here. See this length, say I'll take this length as R1. R1 is inversely proportional to square root of alpha at this point. Say this point is 1. Okay. So what is the polarizability at point 1? Listen, this length is small. This length is small, which means polarizability here is large. Along this line, polarizability is large. Polarizability large, that's why the length is small. What about here? This length. Suppose I'll take this point as 2. See, this length is large, right? Which means length large means polarizability in this direction is small. If polarizability is small, then the length will be large. If polarizability is large, then the length will be small. Is this clear to all? So first we'll start with the rotational Raman spectroscopy. Okay, and very specifically, I'm going to discuss about diatomic molecules. Right? Diatomic molecule. Remember, both homo and hetero diatomic molecules are active in Raman. Both homodiatomic molecule and heterodiatomic molecule show rotational Raman spectrum. Very, very important. But heterodiatomic molecules also active in microwave. So usually for heterodiatomic molecule we use microwave spectroscopy. For homodiatomic molecule we use rotational Raman spectroscopy. Okay, yeah. So this is main information regarding the homodiatomic molecule and the rotation spectrum. Now, the first step is what is the energy formula. You know very well, this formula we have already discussed. Rotational energy F of J. F of J is the usual symbol for rotational energy in wave number. Okay, F means energy, J represent rotational quantum number. F of J is equal to Bj into J plus 1 minus Dj square into J plus 1 the whole square. This is the energy formula in centimeter inverse. What is B here? B is called rotational constant of the molecule and D is called centrifugal distortion constant of the molecule. Okay, so what is B? B is called rotational constant. Rotational constant of the molecule, and D is called centrifugal distortion constant. Centrifugal distortion constant. And remember, if you compare the B value and D value is very, very, very large compared to D. Since D is small, usually this term, the second term, contribution of the second term to the energy is very, very small generally. In the case of rotational Raman spectroscopy, okay, the contribution of this term, right, is very, very, very small. So we usually neglect this term. Okay, if you neglect the centrifugal distortion term, then the energy formula becomes F of J equal to Bj into J plus 1. Okay, so if you use this formula, indirectly we are assuming that the contribution of centrifugal distortion term, right, is very, 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 very small, negligibly small. That's why we neglected that term. Okay, so this is the formula we are going to use hereafter. Then, I can say in the other way, if we use this formula, we are assuming the molecule as a rigid rotor. Okay, now, what about the selection rule? Listen carefully. Whenever we say selection rule, we give two selection rules. One is gross selection rule and the other one is specific selection rule. What is the gross selection rule? Listen, we are talking about rotational spectrum of diatomic molecule. So I'll take a homodiatomic molecule, say chlorine molecule, and I'm applying an electric field in this direction. Okay, if you apply electric field in this direction, listen carefully, along the bond axis now, the molecule is oriented in this direction and electric field is also in the same direction. Along the bond axis, it is quite easy to polarize. Easy to polarize. So polarizability is more along the bond axis. Therefore, polarizability more means distance should be small. So along this direction, polarizability distance should be small. Whereas you are applying electric field in this direction, but in the perpendicular direction here, okay, it is difficult to polarize the molecule in the perpendicular direction. Therefore, polarizability perpendicular direction is small. Therefore, the shape will have larger value here. When the molecule rotates, what will happen? See, when the molecule rotates, it goes like this. Now, electric field is acting like this and the molecule is like this. Now, what happens? In the perpendicular direction, see, it's very difficult to polarize. If difficult to polarize means polarizability is small in the perpendicular direction, but the R value will be large. So from the center, R value is large along this axis because it is difficult to polarize. Whereas along the bond axis, it is easy to polarize. Okay, that is why the distance right along this axis is small. Now listen, see the shape of the polarizability ellipsoid changes, correct? Here ellipse is like this, ellipsoid is like this, here the ellipsoid is like this. Then as the molecule rotates, the shape of the ellipsoid changing, which means polarizability delta alpha is changing. Polarizability is changing. So during rotation, polarizability of the molecule changes. Okay, if polarizability changes, then those molecules are Raman active. Okay, this is what we call as gross selection rule. So what gross selection rule is there? During rotation, if the polarizability of the molecule changes, then that by rotation is Raman active. So this is the gross selection rule. According to gross selection rule, listen, during rotation, if polarizability of the molecule changes, then that rotation is Raman active. Okay, or that molecule is Raman active. Right? Now we'll move on to the next one. Listen. Now we'll move on to the specific selection rule. What the specific selection rule says is that, listen, this specific selection rule comes from quantum mechanical informations, which we are not going to discuss. Okay, we have a concept called transition dipole moment integral. Okay, for transition dipole moment integral to be not equal to 0, okay, then we get this condition, right? So which actually requires some quantum mechanical informations, which I'm not going to discuss that. I'm giving you the rules directly. Okay, this is called specific selection rule. What this rule says is that for a molecule to be Raman active, delta J should be plus or minus 2. Delta J0 corresponds to Rayleigh line. This is Rayleigh. Delta J plus or minus 2 corresponds to Raman lines. Okay. Remember, this is very, very important. In microwave spectrum, see, for heterodiatomic molecule, right? Under microwave spectroscopy, we have discussed this already. Microwave spectroscopy, change in delta J should be plus 1 or minus 1. This is the condition. Whereas, for the rotational spectra in Raman, the selection rule is delta J plus or minus 2. Why plus or minus 2? Listen carefully, I'll give you a simple way of understanding this. Listen, in microwave spectroscopy, we consider only the absorption. Only absorption takes place, or only emission takes place, correct? So, when absorption takes place, angular momentum changes by 1 unit. Whereas in the Raman spectrum, what happens? First, the molecule excited to a virtual state, then it returns back to a new state. right? For the absorption to virtual state, one angular momentum changes. Angular momentum changes by 1 unit. And for virtual state to the final state, another unit of angular momentum changes. So there is a 2 unit of change in the angular momentum. That is why the value is delta J0 or plus or minus 2. Delta J0 corresponds to Rayleigh. Okay, leave it. Plus or minus 2 corresponds to Raman lines. Right? How to understand this plus or minus 2? See, what is the meaning? Listen, suppose I'll take a molecule present in the ground vibrational state of the ground electronic state. A molecule is present in the ground vibrational state of the ground electronic state. In this, we have number of rotational levels, J0, J1, 2, 3, 4, etc. Right? And listen, you know very well, rotational level gaps are very, very small. Therefore, even at room temperature, many rotational states are highly populated. Highly populated. Okay, molecules may present J equal 0 level, J equal to 1 level, J equal 2 level, J equal 3 level. So, population in many rotational states are very, very high. Right? If you pass radiation, incident radiation, molecule absorbs. Suppose if molecule present in J equal 0 level absorbs the energy and goes to a virtual state. Listen, this virtual state is present between this ground electronic state and the excited electronic state. It is between, the virtual state is present between these two. So molecule goes to virtual state, then when it returns back, if it stops at the J equal to 2 level, see, J equal to, its absorption starts from J equal 0. It goes to virtual state and return back to J equal to 2. That means the net absorption is 0 to 2. The net absorption is 0 to 2. Okay, so higher level is 2, lower level is 0, the difference is plus 2. Okay, whereas in the case of anti-Stokes, see, it starts from J equal to 2 level, goes to the virtual state. When it returns back, it goes to J equal 0 level. Right? So here what's the difference? Final state is 0, initial state is 2, so 0 minus 2 is delta J minus 2. Okay, take 2. In rotational Raman spectrum, intensity of Stokes lines and anti-Stokes lines are almost equal. Why? The reason is that, see, Stokes line starts from, suppose I'll take this Stokes line, particular step, right, where it starts from J equal to 0 level. We have some population here. And for anti-Stokes line, see, it starts from J equal to 2 level, but population is almost equal because all J levels are heavily populated. Okay? It is not like vibration. In the case of vibrational levels, ground vibration level has high population. Next level has low population. But in the case of rotation, right, many rotational states are highly populated. Therefore, intensity of Stokes line and intensity of the anti-Stokes lines are almost equal. Right? Energy required for a transition, we use the symbol delta F. What is the delta F? Suppose if the lower level is J, right, molecule goes from J to a virtual state, then it returns back to J plus 2. Okay, therefore the actual transition is J to J plus 2 transition. Right? So what is the energy required for this transition? It's called delta F. Delta F is equal to energy of the higher level minus energy of the lower level. F of J, what is the formula? Bj into J plus 1. Then what is F of J plus 2? Wherever J is here, put J plus 2. B into, in the place of J, you put J plus 2. And here also in the place of J, you put J plus 2 plus 1. So you get J plus 3. Then multiply these two and take B as common. Then you make some simplification. You just make some simplification. You get this answer. B into 4J plus 6. Here you have J square. Here also you will get J square. But we have minus sign here. So J square cancel. You just do it. You will get this answer. Okay. So this is the energy required for a transition. Right. Then the next step is frequency of the spectral line. At what frequency first Stokes line will appear at what frequency second Stokes line will appear, third Stokes line will appear. Okay. Similarly, at what frequency first anti-Stokes line will appear and second anti-Stokes line appear, right? That you can get using this formula. See, frequency of the Stokes line is equal to frequency of the incident line minus energy required for transition, because Stokes lines appear in the lower frequency side of the incident, right? So nu I, you keep this nu I bar as such minus, what is delta F? Delta S is equal to B into 4J plus 6. So this is the formula we are going to use, okay, to find the frequency of the Stokes lines. Similarly, what is the frequency of the anti-Stokes line? Which is equal to frequency of the incident radiation plus the energy required for the transition, because anti-Stokes lines appears in the higher frequency side. Okay, so nu I bar plus B into 4J plus 6, right? So this is the formula we use for anti-Stokes line. Now let me show you at what frequency first Stokes line will appear. S1 means first Stokes line. At what frequency first Stokes line will appear? Very simple, put J equal to 0 here. If I put J equal to 0, this becomes 0, we will have 6 here. So nu I bar minus 6V, nu I bar minus 6V. Yes, first line will appear, okay, nu I bar minus 6V distance. I'll show you in the spectrum. What about the second Stokes line? For second Stokes line, put J equal to 1. If you put J equal to 1 here, 4 into 1 is 4, 4 plus 6 is 10, so you'll get minus 10B. So nu I bar from the Rayleigh line, you subtract 10B. Subtract 10B, at that frequency, the second Stokes line will appear. Similarly, what about third Stokes line? Third Stokes line, nu I bar minus. For third Stokes line, put J equal to 2. 4 into 2, 8. 8 plus 4 is 14. So we get minus 14B. Right? At these frequencies, first Stokes line, second Stokes line, third Stokes line. What about the corresponding anti-Stokes lines? For anti-Stokes lines, use this formula. First put J equal to 0. If you put J equal to 0, this becomes 0. We will have 6 here. So 6B. We get nu I bar.
Sir, 18B, sir.
So in Raman spectrum, rotational Raman spectrum, or in Raman spectrum, we plot intensity in y-axis and scattered frequency in the x-axis. At one particular frequency, incident frequency and scattered frequency are equal. It is called Rayleigh line. Okay, Rayleigh line. Now, the first Stokes line will appear nu I bar minus 6B. So from the nu I bar, this is nu I bar, you subtract 6B. If you subtract 6B, yes, we get the first Stokes line. This is S1, first Stokes line. At what frequency it will appear? It will appear at nu I bar minus 6B. Okay, the first line will appear at nu I bar minus 6B. What about second? So, which means the gap is, this gap is 6B. Am I right? Because this is nu I bar.
Yes, sir.
This is nu I bar minus 6B. So, this gap should be 6B. What about the second Stokes line? Second Stokes line? Where it will appear?
10B.
Nu I bar minus 10B. This difference, observe carefully. This difference is 10B, correct? From the Rayleigh line, the gap is 10B. Gap between Rayleigh line and the second Stokes line is 10B. What about the gap between adjacent line? This is 10B.
4B,
This is 6B.
sir.
Yes, the gap between adjacent line is 4B. Similarly, if you go to S3, for S3, third Stokes line, the value is 14B. Right? 14B, this is 14B. S2 is 10B. Subtract, you get 4B. Right? Same thing happens for the anti-Stokes line also. Anti-Stokes line 1, anti-Stokes line 2, anti-Stokes line 3. Okay, so the point here is spacing between successive Stokes lines. Spacing between successive Stokes lines or successive anti-Stokes lines is equal to 4B. Listen, in the microwave spectrum, remember, in the microwave spectrum of a heterodiatomic molecule, in microwave spectrum of a heterodiatomic molecule, the gap we observed is 2b, correct? The gap between adjacent line is 2b there.
Yes, sir.
Whereas in rotational Raman spectrum, the gap between adjacent line is 4b. Anyway, by measuring the gap, we can find the value of, the gap is equal to 4b. If you know the gap, you can find the value of b. If you know the value of b, you can find the bond length of the molecule. Bond length of the homodiatomic molecule. Okay, so for heterodiatomic molecule, use microwave spectrum, find the bond length. For homodiatomic molecule, use the rotational Raman spectrum, okay, and measure the gap between adjacent line. From the gap, we can find the value of b. From the value of b, we can find the value of the bond length. Okay.